So, welcome everyone. It's my pleasure to introduce Srivatsan Ravi today. He's a postdoctoral researcher in the Department of Computer Science and is interested in the theory and practice of distributed computing. Today, he will talk about how to make in-memory transactions safe. Over to you.
Thank you, Himanta. So this talk is going to be about building and the inherent complexities associated with implementing in-memory transactions. So transactions is, of course, a concept that everyone in the computer science is familiar with, but there are some inherent issues in implementing them inside the memory. And what I will be talking about is the motivation for this programming model, the inherent complexities associated with it, and hopefully several questions for all of us to ponder over. So the background here is, so for those of you who are familiar with sort of the recent trend in the computing industry, we've seen this idea that the number of cores put on a single computing chip has increased since the early 2000s. The so-called Moore's law is no longer valid for us, in the sense that you can't keep writing sequential programs and expect it to give better performance just because you have a faster processor. So you've reached that thermal and physical limit of the number of transistors that you can fit into a single die. And so CPU manufacturers have moved towards putting multiple cores within a single chip. So you've seen this increase of stabilization of CPU frequency, but the increase in the number of cores which are put into a single die. So the bottom line for us from the perspective of an algorithm designer is that programs have to be written for concurrency. So the thread level parallelism in the program will have to be exploited. But of course, what this means is that these processes and threads, they have to synchronize amongst each other, right? But at some point, when all these multiple threads try to access a single piece of data, they reach the sequential memory bottleneck. And now the question for us is, how do you resolve that? And this is a very deep question at the heart of designing concurrent programs. So most of us are aware of these traditional synchronization techniques. So you have this coarse-grained locking technique where you just, if you're implementing a list, you just take the lock on the head, and it's very simple and easy to use. But of course, there's a contention and a sequential bottleneck associated with it, right? There's the single lock, and you really prevent any concurrency happening. Or you can do more fine-grained locking, right? You can take locks depending on the semantics of the application that you're building, and there is a fine granularity, there's great performance, but it's so much harder to verify, and more importantly, it's not easily composable. So you can't take different lock-based programs and sort of get them working in one contiguous piece of program which appears correct. Or you can do this lock-free synchronization where you exploit the hardware primitives that are provided, that provides this sort of fine-grained granularity and great performance, but again, it has the same problem associated with fine-grained locking. It's just so hard to verify the correctness of the concurrent program. You can't ensure the safety of the concurrent program more specifically. So just to sort of give you a background, if you were designing a list-based queue, right? A very simple data structure that we are all aware of, a first in, first out data structure, right? What goes in first comes out, NQ and DQ operations. So if you had to do this via coarse-grained locking, if you implemented it as a linked list, you would simply take the lock on the head of the list and you're good. So what is the problem? So the lock becomes this bottleneck, and if this process holding this lock fails without releasing this lock, then no other process can acquire any operations on this data structure. The sequential bottleneck, and this is a blocking abstraction, this single lock. Or you can do fine-grained locking, right? So in this case, it's a queue. When you're working on different parts of the queue, you can use different locks. But then now the programmer needs to implement these locks in a safe manner. He needs to be careful that he doesn't violate the semantics of what he's trying to implement in the concurrent code. And this is an age-old problem for us. And this turns out to be a verification nightmare most of the times. So it's okay for a simple queue or a stack data structures that we know. But what about more complex data structures for which the sequential behavior is fairly rigorous and hard to specify? Or you can do this lock-free programming where you use these non-blocking primitives like compare and swap and test and set, which are available on modern hardware architectures. instruction set architectures. And you have the same problem with these too, where you really need the programmer to understand the semantics of what he's trying to implement so that he only generates safe code. Verification nightmare. But here's a more real world problem that all of us, I'm sure, as designers of concurrent programs are faced with. So you have two different queues, right? Two independent queues. Now imagine you want to move one piece of element from one to the other, and you want this entire action to appear atomic. So what does this mean? So you want to atomically dequeue from the first queue, and whatever you get from that dequeue, you want to enqueue it into the second one. Now you want this entire action to appear atomic in the sense that no other concurrent process sees that it was dequeued and it wasn't enqueued. So it either sees that nothing happened or both happened. How do you ensure this? Now you could take locks on each of the individual queues and design it explicitly the way you would. But this is not really a universal solution, right? What you really want is something right in the middle, right? With coarse-grained locking, you take that single lock, it's going to be safe, but it's not really going to perform well, it's going to be blocking. But then you have this other extreme with this lock-free programming and fine-grained locking, in which case you're really going to exploit the concurrency. You're probably going to get highly efficient code, but it's much harder to verify the safety of the code. So you want something which is right in the middle, just right Goldilocks, right? And this is where transactional memory as a programming model has really come into the picture for us. So the idea is now that concurrent programming is made very simple as long as the underlying sequential code and the sequential specification is correct. So the programmer himself does not need to explicitly worry about dealing with correctness and deadlocks. Easy composability and verification. Whatever the composable problem that you have, you get this in sort of a black box abstraction, a universal piece of programming model. And the concurrent operations are basically now executed as optimistic transactions with this all or nothing semantics. So either the entire piece of code takes effect or it does not. So imagine how good an abstraction that is. So you get the best of both worlds now. So you have the coarse-grained locking, which is very simple and easy to verify the safety of the code. And hopefully, we can get these transactions to execute concurrently and resolve these conflicts at runtime. Now the purpose of this talk is to talk about what it takes to implement such transactions. More specifically, in this talk, I will only concentrate on the inherent complexities associated with implementing them and where the bottleneck lies. So if you look at it in terms of an implementation, you have these transactions which are accessing these data items like the nodes of a list, which in turn are working on these underlying memory locations with the abstractions provided by the underlying hardware instruction set architecture. So these transactions now just do reads and writes on data items. Now our goal as algorithm designers is to just provide the algorithms for designing these reads and writes. And once you do this, it serves as a universal abstraction. So you can work on any well-defined piece of sequential code instead of explicitly writing code each time specific to whatever you're trying to implement in a concurrent way. So you can do this purely in software, just like designing any other data structure. You can implement these transactions by applying these primitives on these base objects. But what is really cool for us right now is that there is support for executing these transactions as part of the instruction set architecture, which basically extends the classic messy cache coherence protocol. And in this talk, I'll be explicitly concentrating on this. But then there is a problem, right? Even hardware transactions can arbitrarily fail. So what now people tend to do is move towards this hybrid model of transactions in memory, where you first try to execute something in hardware because the hardware is going to be very fast. It's going to give all these safety semantics to you. And if the hardware transaction fails, of which there is a very high probability, simply because of spurious aborts, the size of the cache line is limited. The process executing the transaction may be arbitrarily descheduled at any point of time due to context switching. So you need a backup. The backup being you try to re-execute that same piece of code in software. So this is what we call the hybrid model. And this is pretty much the next generation programming model, I would argue, for writing safe concurrent code. When I mean safe, I'll elaborate on this. It must be that these transactions are consistent. So they're opaque to the outside world in the sense that everything happens without any concurrency bugs that are explicitly introduced as part of executing these transactions. So just in terms of using transaction memory, for those of you who are trying to envision what this programming model looks like, it's quite simple. So you write your piece of sequential code. So in this case, imagine you're just doing your enqueue into a queue abstraction. So you set, implement it as a list, you change the pointers, the next to point to the new node and the new node to point to the new element that you're inserting. This is just a simple piece of sequential code that all of us know how to write. Now your goal, when you try and turn it into concurrent code, all that the programming model requires is to explicitly mark the piece of code that you expect to run atomically with an atomic delimiter. So this is exactly the delimiter which is provided by today's software transaction memory implementations. In fact, for those of you who are familiar with it, the current GCC implementation has support for running in-memory transactions. So the delimiter is just transaction atomic, which lets you write your sequential code, just place this, and the underlying compiler worries about resolving conflicts while ensuring that the underlying implementation is safe. So the concurrent operation in the atomic block is executed as a transaction. So what it would mean is that in this case you're performing a dequeue operation and you're performing an enqueue operation. Normally you would take fine-grained locks if you wanted a real efficient implementation. In this case, you don't worry. You write your sequential code and you just wrap the dequeue and enqueue operations within two separate transactions. And the underlying GCC implementation or whichever compiler that you're using endeavors to execute these transactions concurrently with this all or nothing semantics. So far so good? So the programmer does not need to worry about correctness in deadlocks, or is it? How do we ensure that the programmer doesn't have to worry about correctness and deadlocks? And that's pretty much the goal of this talk, where I'm trying to help you understand what are the inherent challenges associated with implementing these transactions today. Because I would argue that this is the real zeitgeist programming model for concurrent code right now. So in this case, imagine you're inserting and removing into a list, a classic banking transaction, however you want to think of it. You're inserting an element into a set and you're removing an element into a set. So in this case, the head points to a node 1, node 1 points to a node 2, 2 to 3, 3 to 4, and then to tail. So this is the initial invariant that is present. So now imagine there is a transaction, two transactions happening. They're trying to happen concurrently. This is simply like someone inserting and removing some money into your banking account, or however you want to envision it. So in this case, what you need to do when you insert a new element 1 is that the head you need to create the new element, and the head pointer needs to be updated to point to this new element, let's say 1, which is created, and the new element created, its next pointer must be changed to this existing element, which is 2. But concurrently, there is another transaction, of which the first transaction is oblivious to, which is trying to remove the element 2. Right now, you must make sure that there are no dangling pointers at this time. How do you do this? This is what we mean by safety. Right? It's something which is obvious to us, these subtle concurrency bugs that arise. And the question is, what does it formally mean to say a piece of concurrent code is safe, in the sense that nothing happens that could not have happened in a sequential run of this program? Here's another example. So initially we begin with this invariant, two data items, x equal to 1 and y equal to 2. And you have two transactions which are running concurrently. So transaction T1, which is reading this element x, and it's trying to atomically increment it, and it's trying to atomically increment the element y. And there is a concurrent transaction which is basically trying to do 1 by y over x for some reason. So what is the most important thing what is the worst thing that can go wrong here from the design of a concurrent programmer? So the worst thing that can go wrong is that the concurrent transaction only sees a partial update. It sees that x has been updated, but y has not yet been updated. If that is indeed the scenario, what can happen? You can basically envision that this transaction T2, it reads x equal to 2 and y equal to 2, in which case you end up going into a division by 0. So what is happening is that these two transactions, simply by virtue of a bad implementation, are seeing a state of the system configuration which they could not have observed in a sequential run of these two transactions. And these sort of errors are errors which are typically irrecoverable from. And this is really a problem for us. And how do we deal with these sort of errors is basically the challenge of designing safe transactions or safe transactions in memory. So what is safety for in-memory transactions? The safe code must basically protect against these runtime errors like division by 0 or running into infinite loops, simply because the transaction witnesses an inconsistent state of the system configuration. And from our point of view, safety basically means, in very informal terms, that no transaction must witness state that cannot be observed in a sequential execution, even if the processes executing the transaction may fail by crashing. So is that clear? So what it means is that nothing can happen during the execution of a concurrent transaction which could not have happened when the same transaction ran sequentially without any concurrency. This is seemingly a very obvious definition of what is safe, right? The mind tends to envision what is running sequentially. It's much harder to envision the possible interleavings when n different processes try to concurrently access a same piece of memory. So formally, what this would mean for us is that the execution appears opaque. By opaque, I mean I can take an execution, a concurrent execution in which these transactions and these processes are interleaving and accessing different memory locations. And I can reduce it to a sequential execution of these same set of transactions. So every transaction, including the ones that are aborted and are incomplete, must be placed in a total order. And this total order must appear like a sequential run of the same set of transactions. So if you don't worry about aborted transactions, it's this famous definition that I'm sure all of you are familiar with from the database world, which is strict serializability. You can serialize all these transactions, at least the committed ones, without worrying about the state seen by the incomplete transactions. So let's try and understand what this definition means, because it's not immediate to follow. So here you have a transaction T1 which is reading a data item X, and it's returning the initial value of this item, let's say 0. Let's assume all data items have initial value 0. And it's subsequently going to go ahead and read a data item Y. But imagine that just after it reads the data item X, there is a concurrent transaction T2 which writes a new value to this data item X, and it commits. So what this transaction has previously seen has been overwritten by a concurrent transaction. And now I'll schedule another transaction T3 which is writing a new value to this data item Y. Now this transaction T1 is actually reading the state of the memory, and it will see that the value of data item Y is 1, and it's going to return this value. What is the problem with this execution? So the problem here is that the transactions T2 and T3 happen one after the other. So if I take transactions T1, T2 and T3 and place them in a total order, this total order, there must be a total order in which I can justify the response of transaction T1, which returns 0 from X and returns the new value for the data item Y, which is 1. So what can I do? I can put transaction T2 and T3 before T1. So if I put T2 and T3 before T1, I have a problem, right? So T2 happens before T1, but then T1 never sees that new value of X has been updated in the memory. So I can never sort of totally order these transactions. I always get a cycle in this piece of code. So, and this is the scenario even if this transaction T1 aborts. I don't care whether it aborts or commits. It still sees an inconsistent state, a state that could not have been observed in a sequential run of transactions T1, T2 and T3. And as I said, the equivalent sequential execution is to take these three transactions and place them in some total order. So if you try all possible ways, all possible permutations of placing these transactions in this total order, you see that all these permutations result in a cycle a cycle which cannot justify the responses returned by transaction T1 in any sequential run of this piece of code. So, this is what we call a cycle in the serialization. So, this is an example of an execution which is not opaque. So, if you think about just serializability, where transaction T1 is aborted, it's not committed. So, in this case, you're perfectly fine because you don't worry about the state seen by transaction T1, which is actually aborted in this execution. So, now you just worry about transactions T2 and T3. No one is reading any state. No committed transaction is reading state. So, you just say it's serializable. But for all of us who write in-memory transactions, we look for this strong safety property, which is opacity. So, you want the entire piece of code to be opaque in the sense that it's privatization safe. So, no transaction, even the aborted ones, can see a state which cannot be witnessed in a sequential run. And if you think about it, this is sort of obvious, because once a transaction, even if it may in the future eventually abort, if it sees an inconsistent state as part of the program, for instance, the previous example, it could end up doing a division by 0 or running into an infinite loop. And then you're stuck in this error from which you can't recover from. So, in this case, you have transaction T1 which actually goes ahead and commits. So, in this case, you would say that this execution is not even strictly serializable, because now I even worry about the state seen by this committed transaction T1, and I still get that cycle in the serialization. But of course, safety alone is not enough, right? If you're in a distributed system in which nothing ever works is trivially safe, right? We don't care about this. So, what you really want to ensure is that there is progress in the system, which is why we don't resort to the single lock based solution, right? Because it's trivially safe, but it's never actually going to give you progress in the system. So, if every transaction aborts, then you're trivially safe, who cares? But that's really not good. So, you want to allow for as much concurrency as possible. And ideally, you want every transaction to eventually commit. So, they must be able to make progress in parallel. And the goal of this talk is to basically understand what is this cost of concurrency. Are there these inherent limitations to building safe in-memory transactions? So, if you just sort of take a step back, and I want to give you a brief overview of the history of this programming model. So, it first came as a hardware abstraction in 1993 as a modification to the instruction set architecture. And this was by Herlihy and Moss, where they essentially exploited the cache coherence protocol and gave a proposal for executing hardware transactions in memory. But then this proposal died. People made some proposals for a software transaction memory implementation, which was static, where you could specify the data items that you are trying to access atomically a priori. And eventually you move to a more dynamic model, which is what is prevalent today, where even if at the start of the transaction you don't know all the data items you're eventually going to access, you can resolve these conflicts at runtime. And now, as I said, we've moved towards this hybrid model. And the main reason for that is that today's Intel chipsets, if you buy the latest chipset today, the Haswell chipset, has support for in-memory hardware transactions. And once Intel or one of these hardware manufacturers put these instructions in their instruction set architecture, they don't take it out simply for backward compatibility. So, this model is here to stay. And what is important and what is even more good for people like me is that we don't yet know how to develop efficient use of this instruction set which is now given to us. And as we'll discover in this talk, there are some inherent limitations we just can't overcome. So, we have to find ways to circumvent those limitations. So, this talk, as I said, is about this inherent limitations of these hybrid transactions. So, when I say hardware transaction memory, all you have to imagine is a modification to the existing cache coherence protocol, which has support for caching transactional state. So, you keep this additional state which is added as part of a transaction in some tracking set, and when this tracking set gets invalidated, you know that the hardware transaction has incurred a conflict, which means the transaction is going to abort. So, you get this consistency and safety and conflict detection for free as part of the hardware transaction, and it appears to execute atomically in hardware. So, basically an extension to the cache coherence protocol, and this is true of both the Intel Haswell chipset and the IBM Blue Gene Q processors, which also have hardware transactional support. So you have this fast part transactions which are executed entirely in hardware, which are exploiting cache coherence. But then, as you can imagine, anything which is executed purely in hardware comes with fundamental limitations. And in this case, because you're exploiting cache coherence, you're limited by the size of your cache hierarchy, your cache line. Whereas anything executed in cache potentially has a very short lifetime. You can't execute these very long running transactions because the process executing the transaction will be descheduled. And you may simply get aborts due to these spurious reasons, because there is some other piece of data in your cache line with whom you don't have any actual conflict, but that's just going to be aborted because of another transitive transaction running concurrently. And so you have all these problems with running transactions in hardware. So you can't just expect to run everything in hardware and have everything running safely and fast, which is why we exploit the need for a slow path in which we execute the same transaction purely in software as just a piece of data structure. This is typically for these long running hardware transactions in the cloud, as you can imagine, which is fairly more reliable. But then it's much slower in execution time, obviously, right? Because you're not executing it in hardware. And the interleaving of these two hardware and software transactions make it very hard for us to verify. So for the purpose of this talk, I'll call the hardware transaction the fast path and the software transaction the slow path. So as part of this model, you have these direct accesses and cached accesses in which the slow path transaction directly modifies the memory. And the hardware transaction basically caches everything and puts it into its tracking set of cache coherence in order to be able to invalidate whether a memory location previously accessed or written was concurrently updated or read by a concurrent transaction, in which case you get automatic conflict detection. As I said, for slow path transactions, they operate directly on the memory state. So it's what we call direct access. And these fast path transactions basically put everything in this tracking set, and like in any cache coherence protocol, there's a shared and exclusive state. So if you just want to read something, you just put it in shared mode, in which only if it's concurrently updated, the hardware transaction fails. But if you're writing something, obviously even if concurrently someone reads it, the hardware transaction is aborted. Yes? So the slow path is essentially a transaction which is implemented purely in software. So the fast path is one in which you directly use the instruction set extension which is provided by the chipset. Sorry?
If there's a question, please use your microphone.
Please use your microphone.
Okay. So my question is, with the cache coherence protocols in place in the hardware, like Tomosolo is in place, I'm not understanding what the difference is between these two.
So you have a fast path transaction in which you execute everything using cache coherence. That's what I call fast path.
All right.
And slow path is one when you don't use cache coherence and you write the piece of code explicitly like any other algorithm.
So you're writing directly to memory.
Exactly.
Okay.
So that's what I call direct state and cache state.
Thank you.
So you have these tracking set aborts in fast path transactions because you're working directly with cache coherence, right? You get this automatic contention detection if someone concurrently accesses the cache state. So in this case, you have a fast path transaction T2, which is writing to a base object B, which means this object can be cached in exclusive mode. And now if you have a concurrent any transaction which is even accessing this memory location, then automatically you know that the fast path transaction T2 will be aborted, as opposed to designing it in slow path where you have to explicitly validate this. So this is the advantage when you're exploiting the hardware cache coherence explicitly. So the tracking set is invalidated and you know that this fast path transaction T2 will abort without violating safety. And similarly, if you have a fast path transaction T2 which is simply reading this memory location, it's accessed in shared mode. And if a concurrent transaction simply writes to it, only then is the fast path transaction T2 invalidated. And in this case, it's going to abort. So if you envision it, the hardware gives you all this safety properties for free in essence. The software doesn't. In software, you explicitly have to write code to detect this. But the trade-off here is that the fast path transaction is going to fail most of the times. And you can't actually give any provable guarantees on when this hardware transaction or the fast part transaction is going to succeed, which is why you try to re-execute that same piece of code in the failed hardware transaction in software, which is what we call the hybrid model now. Yes?
So when it fails in the hardware, does it
Go
automatically
ahead,
run
Ron,
the
use your
software?
microphone.
Okay. Does the software always run in case the hardware fails, or only when the hardware fails?
Well, this is down to how you implement this hybrid implementation. So there are different implementation strategies, but the most basic strategy is you try the piece of code as a hardware transaction for X number of times, typically a threshold which people have estimated purely via experiments. And if you fail after these subsequent number of thresholds, you execute that same piece of code as a software transaction. But what is important from the point of view of safety is that you can imagine at any step in the execution that there are hardware and software transactions running concurrently, which for some reason are trying to access the same memory location. And both of them have different mechanisms for detecting safety violations. The inherent challenge for us in the hybrid model is how do you detect it and what is the cost of detecting the safety violations. Yes.
Yeah, I have a question. In the previous slide, we say that if T2 cannot be concurrently executed with T1, then, as you said, T2 will try a couple of times and then we'll switch to the software mode.
Yes.
But it's not guaranteed that in software mode T2 and T1 won't have a conflict,
It's
right?
not guaranteed, yes.
Uh-huh.
We are not guaranteeing eventual commit.
Mm-hmm.
We are only guaranteeing some sort of progress. Progress which basically says if eventually there is no conflict, maybe you'll commit. But I haven't yet gone into the details of this progress. We are still concentrating on safety right now. So in this case, what is important for us to take away is that the fast part transactions, they appear to execute atomic. So they just happen in this one single indivisible point in time. And it's up to the software transactions to detect this. So in this case, you have this fast part transaction T2, it's either aborted or incomplete, in which case the concurrent slow part transaction will assume that it's actually running alone because it just doesn't see this concurrent fast part transaction. It only sees it when the fast part transaction actually succeeds. And similarly, the case when the other transaction is a fast part transaction, right? It's only when the fast part transaction actually commits is that state actually reflected in the system configuration. If it's incomplete or if it's aborted, the state never is reflected in the system configuration. It's like that transaction never took place, which is the most important thing for us for safety, right? You need this all or nothing semantics. Either everything happened or nothing happened. But what is the problem here? So the problem here is that you can't just use the fast part transaction, the hardware transaction, just explicit loads and stores on the memory locations that you're trying to do, right? So you need to explicitly instrument the hardware transaction code to detect additional metadata. What do I mean by this? You need to be able to know that there is a concurrent slow part transaction, which for some reason is very slow, right? But you need to be able to detect this because if a slow part transaction starts but not yet finishes, and then a fast part transaction comes, and like in the example that we saw, it reads a partial state, then you have a problem. Now the question for us is how much do we have to instrument the hardware transaction? Because more instrumentation means that you're adding more into your cache line. You add more into your cache line, there is the more chance of aborts. The more chance of aborts, lesser performance. So here's a simple example which I was alluding to. So you have a slow part transaction. Now remember, this is not atomic, right? So this is trying to write to two memory locations X and Y, but it's in a partial commit state. It's just that the process executing the transaction is very slow because we are in an asynchronous world, right? We are inside a multi-core machine. There is no bound on when these processes are going to take steps. In fact, by asynchrony here, I mean there is no concept of time. There is only causality. So you know something has changed only when the system configuration changes. So in this case, you have the slow part transaction, which is in this partial commit stage, and it just sleeps, right? It's got descheduled or whatever. And now I bring this fast part transaction, which is trying to read X. Now at this point, this fast part transaction, which is just doing a load to the memory, has to make a decision on whether it's going to read this partial state in the hope that this slow part transaction will eventually commit, because if it doesn't commit, it could not have read the state. And if it did commit, there is no guarantee, there is no guarantee for this fastpath transaction T1 that it's actually going to commit at that point. So the best thing it can do is to be able to instrument, you can instrument these loads with some additional metadata, which you can force the slow path transactions to also write to indicate that, look, I'm in a partial commit state. I haven't yet fully completed my transaction, which allows the fast path transaction to detect the presence of this concurrent slow path transaction. And in fact, what you can show is that even if you need some very basic progress, right, you commit only if there is no concurrency. Even if you want some property like this, you need instrumentation. And I'll quickly go through this example. In fact, what it says is that you need some amount of instrumentation in your hardware transactions. So with the same example, now imagine you first read a data item Z, you return the initial value, and then you're trying to write to X and Y. Right? You bring it to this partial commit when X and Y. X is committed but not yet Y. And now you can force a new fastpath transaction which comes later. The timeline goes from left to right here. Okay, you need to envision it from left to right, time flowing that way. So the slow path transaction is just slow, literally. It stops after a partial commit. And then it takes one more step. And then if the fastpath transaction comes and reads Y, it returns the new value. So far, so good. But then what can happen is that if the code is uninstrumented from the fastpath side, I can insert another fastpath transaction T3 here, which is reading X. But at this point, X has not yet been reflected in the system state. So it just returns the initial value. And now I can insert another fastpath transaction, which is writing 1 to Z. And this transaction also goes ahead and commits. So you see that I have transaction T0, which is reading an old value of Z. It's partially committed to X and Y. And then I have 3 fastpath transactions which are uninstrumented. They don't see the presence of this concurrent slow path transaction. They just see the system state. And one of them returns the old value and the other returns the new value. What is the problem? Is this a safe execution of this concurrent program? And the answer is no, because I know that the slow path transaction must commit. Right? I must treat it as committed because there is a fastpath transaction which actually returns this value. But in this case, there will be a cycle in the serialization, because the only way I can justify this in any sequential run is that I place transactions T1 and T3 before transaction T0. Why? Because transaction T3 returns the old value of X. So it must appear to have happened before transaction T0. But if transaction T3 appear to have happened before transaction T0, even transaction T1 must appear to have happened before transaction T3. But if transaction T1, which writes a new value to Z and commits, this value must be seen when transaction T0 actually tried to read Z. So you see, there is no way I can place these 4 transactions in one total order which will justify the response of X, Y, and Z. Was that clear? And what this really tells us is that you must instrument the hardware transaction. And this is where a lot of our overhead comes in. And in fact, this is even for some very weak progress like sequential. So ideally, what you want to say is that only if, let's say, you're inserting and removing into a list, right? So if you're inserting 1 and removing 5, right? There are these 2, 3, and 4 in the middle. There's no real conflict in this scenario, right? So ideally, you expect the 2 transactions which are inserting 1 and removing 5 to run concurrently without any conflict on the memory. This would be the ideal progress guarantee for us, or something realistic. This is what we would call progressive. So sequential here being, you just abort due to a concurrent transaction. And even in this case, you need instrumentation. And progressive would be only if there is a real read-write conflict on the data items that you're accessing. And in fact, what we can show is that even in this progressive case, of course, even in the sequential case, you have this instrumentation that you must incur. But in the progressive case, you actually have a linear amount of instrumentation that you need to incur. So for each memory location that you access, you need to access an additional piece of metadata that you must place into your tracking set and cache line. And this is a huge overhead and a huge step back for us when really designing hybrid transactions, because you just aren't going to get sufficiently good enough performance to justify the application developer to migrate from legacy lock-based code, which has been working for 20, 30 years, to this new programming model. So the real cost now is that these fast path transactions may be aborted even by slow path transactions which are not conflicting at all with you, and you still suffer because of this, because there is no real progress now. But if you do need some progress, then you have to incur this linear instrumentation cost of placing more stuff into your cache line. Now, whether this experimentally translates in terms of real performance, in terms of overhead to your concurrent code, this is up for debate. This depends entirely on the cache hierarchy, the size of the cache line, so many other parameters. But what about the cost in the slow path? And what we can show is that even the slow path incurs a significant cost. So what will happen is that the fast path transaction may be aborted by non-conflicting ones, or the fast path incurs this linear instrumentation cost. But even the slow path will have to continuously validate itself, whatever it reads. Let's try and look at an example for this. So what you actually have even for the slow path is that if you want this progressive property, you're going to incur this validation cost. Each time you read something, you must go back and check if whatever you read before has not been changed since, which is intuitive. So imagine here that you have this transaction TM, which is writing a value 1 to x. This is a fast path transaction. This transaction will go ahead and commit. And now imagine you have a long running transaction, right? Imagine you searching through an Amazon database or anything, one of these transactions. You're reading m distinct data items. So you want to get the value of them. So you read x1 to xm minus 1 and you get the initial value. And then you read xm and you see that the state of the memory is no longer the initial state, and you return the value 1. So this is a slow path transaction. It doesn't exploit cache coherence. So you have these reads which are pretty much invisible, right? Reads don't modify the memory. At least ideally we wouldn't expect the read implementation to modify the state of the memory. And as you can imagine, this read of xm must actually return 1. This can't return 0, right? Because a previous transaction changed the state of this memory of xm. Now, if you move that fast path transaction to run after the read of xm minus 1 and concurrently with xm, this read of xm will still return 1, right? Because it can't distinguish the two scenarios. So first m minus 1 data items return the initial value. The mth data item returns this new value. But what if there is a concurrent transaction which is writing to x1 after x1 has been read by transaction T0? Now this read of xm as part of the transactional implementation has to make a choice. So it has 3 options. One is that this transaction aborts, the read aborts, it just doesn't return a value and says that this transaction failed. The other is that it returns 0, the initial value of xm, or it returns 1, which is the new value written by a concurrent fast path transaction. So what must it do to detect this scenario? So in this case, this slow path transaction as part of your implementation must go back and read the state of the memory of the previous transactions that have been read to check if they haven't been invalidated. So in this case, transaction T0, when it performs the read of xm, must actually go back, keep local state of all the memory locations that have previously been read, and check if any of these memory locations have been changed since it last read them. In essence, it must get an entire snapshot of the memory during the execution of this long running transaction. But now we have a problem. The problem here being that if it does return 1, there is a cycle now. It can't return 1. That's out of the question. Because if it returns 1, then I have Tm and T1, which must appear in any total order like a sequential execution to have happened before T0. And I can't justify the response of x1 returning 0 and xm returning 1. It can never happen in a sequential execution. This is not a safe piece of code. But in the worst case, what can go wrong is that I can stuff m minus 1 different transactions, each of which are writing from x1 to xm minus 1 concurrently. Right? This can perfectly well happen. These are writing to different memory locations, and they are all expected to succeed. The cache coherence won't detect any conflict. And now what must this read of xm implementation have to do? As I said, it must go back and verify not just whether x1 has changed, it must verify if anything from x1 to xm minus 1 has indeed been changed. So in the worst case, I force this read operation to access every memory location that was previously read by this transaction. And this is an extreme overhead for long-running transactions, which are of course extremely prevalent in today's cloud applications. And the problem here is that this read of xm is going to access m minus 1 distinct memory locations. So there is this huge complexity that I incur for the slow path transactional implementation. And if I don't incur this, I violate safety, and I end up causing all these runtime errors, potentially depending on the underlying program code. And if you sort of proceed by induction here, you can basically see that there is a quadratic complexity here, right? Because each read has to go back and check if the previous reads have been changed. And iteratively, this sums up to be quadratic in the size of all the memory locations that I'm accessing as part of this long-running transaction. And the big challenge for us as algorithm designers is how do we overcome these fundamental limitations? How do we move to this programming model which is so simple and easy to use, which is here to stay, but circumvent these fundamental limitations? So just to take a step back, as I said, even in the sequential case, you have this overhead, and even with the slightly more concurrency scenario, you have this linear cost that must be incurred on both the fast path side and the slow path side. Else, you don't get any concurrency. So this is the price that we must pay for writing safe concurrent code which can work in any sequential application, but in a safe manner without introducing runtime errors. So with that, I'll move to my what I have to say as my concluding remarks. What I'm going to argue is that the hybrid model is fundamental. So it is here to stay. The days I would argue of programming essentially using these other programming models like MapReduce or any of these other programming models are eventually, we're going to move towards this, especially for these in-memory high performance applications. And the main reason here is that there is hardware support. There is hardware support in today's Intel chipsets. There's hardware support in today's IBM chipsets. And of course, we know that we are always going to be limited by the size of your cache line, which means that you're always going to expect the code to be re-executed in software. So the hybrid model is fundamental. But of course, writing safe transactions in the hybrid model comes with these huge inherent limitations. The big question for us is how to circumvent these inherent costs. Open challenges for all of us who are designing these. So for those of you who want to play around with the current GCC implementation, you will see, write a sequential implementation of a queue or a stack or a list set, and take the most efficient fine-grained implementation of the same data structure and implement the same data structure, the sequential code, wrap it around the transactional delimiter on GCC, and you will see a noticeable gap in performance. The question for us is how to bridge this gap. The hybrid model is one step towards bridging that gap, because you expect in majority, at least when there is not heavy contention in the cache line, that most of the transactions are going to execute in hardware, which is going to be noticeably faster. But this isn't always the case, especially for applications which have huge sequential bottlenecks. And there are lots of fundamental open questions in terms of choosing I mean, the workloads I presented in this talk, they are pathological workloads, worst case scenarios. Maybe this isn't always the case. So we want to dynamically derive implementations depending on the workload. We need efficient formal methods and verification techniques. And more importantly, understand the impact of cache hierarchy and the memory model. Different instruction set architectures have their own different memory models, which specify what values loads and stores can actually return. So the big takeaway more than anything here is that you cannot violate the safety of concurrent code. This is a given for us, right? If you do this, if you do sort of don't design implementations which are sort of have these strong safety properties, then you have to explicitly patch them using sandboxing or these other techniques which are very ad hoc. So you can't compromise on safety. But what use is safety if there is no performance? But the hardware model does come with some inherent limitations, the hybrid model specifically. The question for us is how to circumvent these limitations. There are tons of ideas which are currently being explored for this. But my purpose in this talk is not to disillusion this programming model, but for us to understand what are the inherent limitations so that we can efficiently overcome these limitations. And there are tons of ways to overcome these limitations, which I'm happy to talk about offline. But as I said, I'll reiterate the significance of this programming model, which I would like to claim is here to stay. And it has support from hardware manufacturers and fits about in developing just about any application with a well-defined sequential specification. And that's all I have to say today. Thank you.
Any questions?
Yeah, I have a basic question about performance increase. So what is the performance improvement if we use this model?
Depends on the application, right? So for, let's say there is a data structure for which we don't know any efficient concurrent implementation, right? We haven't developed a fine-grained concurrent implementation for this, in which case I would argue that go towards this because you're definitely going to get some performance improvement. But for data structures for which we have 10, 20 years of research into how to make them efficiently concurrent, those implementations, especially like queues and stacks, we know to outperform the hybrid model, the hardware transaction memory model. But we should also take this with a grain of salt because we've just got this instruction set architecture. Hardware transactions just came a little over a year ago. And the research community hasn't spent sufficient time in really getting the best out of it. We have some fundamental limitations. For some applications, it looks good. For lots of applications, not yet. But that's because we still haven't moved. We haven't gotten the best, most efficient implementation right now. But if you look at the STAMP benchmarks, the Stanford benchmarks, you will see that for some applications like k-means, it's slightly okay. But also it depends entirely on Haswell versus IBM chipsets. They have different cache hierarchies, different memory models, and we are yet to understand the interplay of all of these parameters to get a deterministic answer on real performance.
Any questions? Thank you very much.
Thank you.